So today we are going to learn the strengthening mechanism and the yield point phenomena. So just a little background of that. Science and technology is based on three axioms, and one of the axioms of science is that every phenomena can be explained in the language of mathematics. Okay, but anyway, we can see that there are so many things in the nature which we cannot mathematically quantify. Is it not? But science says that every phenomena can be explained in the language of mathematics. So, for example, we can say how much pain you are feeling, how much love you are feeling in your heart. You cannot mathematically quantify. But science says that every phenomena can be explained in the language of mathematics. So, based on these axioms, these mathematists were trying to write mathematical expression for mechanical properties of material. For example, strength coefficient, yield strength, ultimate tensile strength, and so on. Based on these axioms that everything can be quantified in the language of mathematics. So what was happening? Whatever they were getting from mathematical expressions and whatever they were getting from experiments, there was no match, and it was a multiple of around sometime 100 or sometime 1000. So there was no match. So after some time a conference was called, and different scientists discussed that what is the problem with our mathematical formulation. So they came to the conclusion that maybe our mathematical approach is correct, and maybe none of the material is perfect, and every material is having defect, and when we apply load on the material, these defects start coming out. People called those defects at that time dislocations. So the hypothesis that formed was that every material is having dislocations, and when we apply load on the material is not failing, these dislocations are coming out, and it appears that the material has failed. So one of the visualization of the dislocation we can see now.
The plastic deformation of metallic materials occurs by the motion of dislocations. Let's see how this happens. Around the dislocation line of an edge dislocation, there are lattice strains, compressive strains above the line where the atoms are squeezed together, and tensile strains below the line where the atoms are pulled apart. When a shear stress is applied, the initial extra half plane of atoms is forced to the right. If the applied shear stress is of sufficient magnitude, the interatomic bonds of the plane next to the extra half plane are broken. This process is repeated for other atomic planes until the extra half plane emerges from the right surface of the crystal, forming an edge that's one atomic distance wide. Macroscopic permanent or plastic deformation corresponds to the formation of ledges resulting from the motion of large numbers of dislocations.
So, as we discussed, that millions of dislocations will be there within the material, and when we apply load on the material in any direction, dislocations within the grain present in that direction start moving. So as just now we have seen that there are dislocations in every material. So let us say there is an edge dislocation here. That is an edge dislocation, and this is an extra half plane, and here is the location site. So when we apply load on the material, so once the load exceeds a certain value, this bond will break and this atom will connect to this. This is called jumping of dislocation. And when the load, we continue to apply load, finally the dislocation will come out. So when the dislocation comes out, we say that yielding has begun in the material and material has failed. So Let us say if I create some obstacle in the movement of dislocation, somehow if I create some problems in the movement of dislocation, so larger stresses will be required to bring the dislocation out. So material will yield at higher stresses. So we can say that strength of the material has increased. So any activity which creates obstacles in the movement of dislocation will increase the strength of material. So the movement of dislocation and the type of dislocations present in the material decides the mechanical properties of any material. Alright. So we are going to discuss now the strengthening mechanisms. Strengthening mechanisms. What are the different ways by which we can increase the strength of any material? Alright. So those who have studied mechanical engineering, the first answer comes from their mouth is that one of the answers they think of is heat treatment. But heat treatment is limited only for medium carbon steel. Every material cannot be heat treated to increase their strength. But there are three different ways by which we can increase the strength of any material. And one of the methods by which we can increase the strength of material is alloying. So, as we were discussing previously that alloys are always stronger than the pure material. We discussed a lot of time. Alloys are always stronger than the pure material. And one of the very beautiful example that can be given is gold, 100% pure gold, we cannot make any ornament out of it. We add impurity of copper into it. We add impurity of copper into it to make it strong. Otherwise, as soon as we are making ornament, it will break. So alloys are always stronger than the pure material. So what exactly happens with the material? That's what we are going to see. So when you alloy any impurity into the material, there are two options. First is the impurity atom will occupy the interstitial site. Alright. So let us say these are host atoms, and this is interstitial void, and some impurity atom occupies that position. So generally this interstitial void is much smaller than the size of any atom. Interstitial void is much smaller than the size of any atom. So when the impurity atom fits in, these host atoms will experience compressive stresses. Suppose the space is not sufficient anywhere and some foreign impurity atom goes there, it will try to create compressive strain field in the host atoms. And let us say if the impurity atom occupies the substitutional site, okay, again there are two possibilities. One possibility is that substitutional size is small. Size of substitutional impurity is small. And another possibility is that size of substitutional impurity is bigger than the host atom. For example, let us consider this case. There is a regular atomic arrangement of any material, and large size impurity atom occupies some substitutional site. Large size substitutional impurity occupies the position. So what will happen, What will happen? This we can understand by a very, very beautiful example which we experience in India. That especially for railway reservation, there is a long queue. There is a long queue for railway reservation. So father and son went for making the reservation. So initially son was in the queue. Alright? And generally we know that the queues are very long and sometimes it takes 1 hour or 2 hours just to get the ticket of railway. So initially son went into the queue and after let us say half an hour, son was exactly in the middle. And it was a long queue. So then son said, I am tired, I want to come out. Father, you come. So son comes out. Father was a fat man. When father enters exactly in the middle of the queue, which strain the people will experience? Compressive stress. Isn't it not? So large size substitutional impurity will create compressive strain field in the host atoms. Is that clear? And let us say when the substitutional impurity size is smaller than the host atoms, substitutional impurity is smaller than the host atoms, there will be some extra space created. So these host atoms will try to occupy that position. For example, there are bricks which are kept one over another without cement. Somewhere from the middle, take out one brick. So whatever space that has been created, the bricks will try to occupy that position. Is that alright? Same thing will happen with the atoms. So these atoms will experience tensile strain field. A small size impurity atom produces tensile strain field. A large size impurity atom produces compressive strain field. So by allowing any material, either tensile or compressive strain fields will appear within the material. So as the dislocation is moving, these strain fields act as a barrier in the movement of dislocation. So larger stresses are required by the dislocation to cross through these stress barriers. That's how strength of the material increases, because yielding will appear at much higher stress. Because what is the yielding? As the dislocations are coming out, that is technically called yielding. So when the stress fields are present in the material, larger stresses will be required by the dislocation to come out. So any obstacle created in the movement of dislocation increases the strength of material. Is that clear? So alloying always increases the strength of material, because either tensile or compressive strain field will be created in the material. Alright? Second method of increasing the strength of any material any material is work hardening. Work, or it is also called strain hardening. So what is work hardening or strain hardening? You must have observed that on stress strain diagram, stress strain curve, yield point, this is ultimate tensile strength point, this is yield point, and this region is called region of work hardening. Meaning, beyond yield point, when we would like to deform the material further, you require larger and larger stresses. It means somehow the material is becoming stronger from within. Somehow the material is becoming stronger from within. So to deform it further, you require larger stresses.